are starting our second week's lesson with sources of magnetism. In other words, we are going to talk about how do we generate magnetic fields. So our learning outcome will be to use Biot-Savart's law to determine the magnetic field at a point due to a moving charge and due to current, and determine the direction of magnetic field due to a moving charge and current using the right hand grip rule. Also, we'll be able to calculate the force on an electric charge due to the magnetic field. So let's talk about magnetic field. You should be familiar with magnetic field, and it is analogous to the electric field. If we have a magnet that is producing a magnetic field, it will generate field lines, and the field lines are also vector quantities. They are just the lines of force. Any point along the field line shows you where a test positive north pole will move if it is placed there. Remember, if we place a north pole here, then the north pole here will repel it, so it will move away from the north pole. So magnetic field lines move from north pole to the south pole. You can see various forms of magnet that are creating magnetic fields. So let's compare magnetic fields and electric field. They have so much in common, and important things to distinguish one from the other one. When it comes to the sources of these fields, electric fields are produced by electric charges, whether they are stationary or moving. And when it comes to magnetic field, they are created by moving charges. Moving charges. If a charge is moving, then a magnetic field will be created around it. When it comes to the field lines are directed from positive charges to negative charges. It will be the direction of test positive charges. So similar to the magnetic field, the field lines will be directed from the north pole to the south pole. Indeed, it will be the direction of a test north pole placed in the field. So if you place a north pole in the field, the north pole will repel, and then the south pole will attract the test pole, north pole. The test north pole. So as you saw from the previous slide, it's analogous to this one. It's similar to this. Now, forces in the fields. When it comes to the materials, that will experience forces in the fields. When it comes to the electric field will apply forces on electric charges. When it comes to magnetic field or bar magnet will apply forces on magnetic materials or another magnet. In other words, if another charge is moving, that will also experience another force in the magnetic field, because the moving charge has also produced magnetic field around it. It becomes like a magnet. Then the force direction, we are very familiar with these terms. Like charges repel and unlike charges attract. When it comes to magnetic field, it is like poles repel and unlike poles attract. Don't confuse the poles and the charges. Force laws. Coulomb's law applied to the electric field, and Biot-Savart, we are going to talk about this. Biot-Savart's law applies to the magnetic field. Then when it comes to the notation, we have electric field strength, which is the E, compared to the magnetic flux density, which is the B here. We are going to use these two throughout our course. Then electric flux, we've met this one already. Sorry, we have the electric flux being the E multiplied by A. Take out the D. Then the magnetic flux is similar. They are analogous. When it comes to the Gauss law, we have Gauss law for the electric field, and it's given by that one. We've spoken about this one in earlier videos. And the Gauss law for the magnetic field is given by this. Now, how do we produce electric field? You can see here a positive charge that is moving in this direction. If the positive charge is moving in this direction, then it will generate magnetic field around it all over. We can determine the direction of the magnetic field, and we can also determine the magnitude of the magnetic field at any point. In this particular case, we are considering the point P here. We can determine the magnetic field, the strength of the magnetic field, using this formula. B is equal to whatever it is, but we should pay attention to this variable here, this vector here, which is the speed at which the particle, the charge is moving with. And this one is a unit vector in the direction of the point that we are considering. You see, I've told you magnetic field will be generated all over, but you take a point and you calculate the magnetic field at that point. You can also calculate the magnetic field at this point. You can calculate the magnetic field at this point, or the point. Look, the magnetic field along the line in which it is traveling is 0, because at that time the radius or the unit vector will be along the direction of the charge itself, so it will be 0. Then this is the magnitude of the charge, the quantity of charge that is moving. If it is 1 coulomb, 2 coulombs, or whatever, you place it here. Now we have a constant here, which is called the permittivity of free space. We can have permittivity in different materials, but if it is in free space, we use not here to refer to the permittivity of free space. It's a property of free space that is related to magnetism. Alright, so we can calculate the magnetic field at point B. This one will be the distance from the charge to the point. Okay. Let's take an example. So the charge is 6 coulombs and the speed of the charge is 8 by 10 to the power 6 meters per second. And this speed is in the direction of y-axis. Now we want to find the magnetic field at this point in the Cartesian plane. At this point in the Cartesian plane. I think I simplified this. I used x equals negative 3, y equals 1. I don't know why this one is still appearing. Ignore this side of the point. We want to get it on the Cartesian plane. Now, the first advice that I will give you is to picture the position of the charge, its direction, and then the point where you want to calculate the magnetic field. So here we are. The particle is moving in this direction upwards, and it is moving with this velocity. The vector distance or the displacement distance will be from the charge to the point. We can calculate the unit vector and then do the calculation. Let's go. So this is the equation we are going to use. This is the equation we are going to use. This is the quantity of charge. This is the velocity. Cross. This is a cross product. We are multiplying two vectors, so it will be the cross product. Let's go through each one of them. This is the charge itself. This is the velocity. We talk about the vector itself, the vector, the displacement vector. That's the vector from the charge to the point where we need to calculate the magnetic field. And it is given as x equals negative 3, which is negative 3i, plus y equals 1, which is j meters. Okay. So we can calculate the unit vector from here, or the magnitude of the displacement. So this is the displacement. The magnitude will be this one squared plus this one squared, or under square root. Indeed, I'm going through this example as if you don't know anything about vectors. So I'm using this one also to show you vectors and vector products. Is that okay? So just pay attention. I'm going through step by step just to make sure you understand this one. The subsequent ones, I will just explain and give you the guidelines and you'll be able to do them yourself. Okay, so we have the magnitude of the vector distance. In other words, this one. Let me show you. So the magnitude of this distance, that's what I've calculated here now. Yeah, this is 3.16 meters. So having calculated the magnitude, we can now calculate the unit vector in that direction, the unit vector. And how do we do that? It will be the vector itself divided by its magnitude. So this is the vector, the displacement vector divided by its magnitude. It gives us this. That's what we are going to use to make the dot product here. Let's continue. So we are now going to calculate this dot product. When we are done, we apply all the other products here and we will be done. So the cross product here is like multiplying the velocity. The velocity here is along the y-axis. If it's along the y-axis, then it will be 8 times 10 to the power 6j cross the unit vector. This is the unit vector. We just calculated it. You remember? This is the unit vector. R cap is different from R arrow, which is the vector itself. Okay. So we are multiplying it, we are cross multiplying it by the unit vector. And I want to keep this factor out and use the 8 here to cross multiply. We multiply it as if we are expanding, but we are still going to do cross multiplication. So 8g multiplied by negative 0.95i, 8g multiplied by that. Then we are going to use 8j multiplied by 0.316. That is it. Now when it comes to cross products, just remember this cycle. I mean, you'll be taught in a different way, but this cycle makes it very, very simple. We have I, J, K. If we cross I and J, we get positive K. If we cross J and K, J first before K, then we get positive I. If we cross K and J, K comes first before I, then we are going to get positive J. In any situation, if the reverse comes, like we have K cross J, then we are going to get negative I, or J cross I, then we are going to get negative K. So cross product is not commutative. It's not commutative. You can't interchange it. That's 8J cross negative 0.95I. If you change it and make it negative 0.95I cross J, you get a different thing. You get a negative value. So we can't interchange cross products. Just as they are, cross them. Okay. So let's continue. So 8J cross negative 0.95I. We multiply the magnitude 8 times negative 0.95 and get 7.6. And we cross the unit vectors. That's J cross I gives us K. So J cross I gives us negative K. This should be negative. And that negative will also cancel out this negative here. And we get positive 7.6 K. If we cross a unit vector by itself, like J cross J here, we get 0. J cross J, that will give us 0. I cross I gives us 0. K cross K gives us 0. So here is the case. 8J cross 0.316J. JJ, if we cross it, we get 0. So that's it. So all that we've done, our result will end up being 7.6 times, this one is times 10 to the power 6K. So this one is doing the algebraic multiplication. So there is nothing like cross products, because this one doesn't have a unit vector ijk by itself that you see it is cross multiplying. It's just a scalar multiplication. So don't confuse this times here with this times here. This one is multiplying a vector and a vector. So the cross product of V, the velocity, and the unit vector gives us 7.6 times 10 to the power 6K. Let's move on to find the magnitude of the fluid. So substitute everything now, and you can check it yourself. We are going to get 4.57 times 10 to the power negative 7 K Tesla. So the magnetic field will be in the direction of K. It will be in the direction of K. It will be coming out of the page. If we should draw the Cartesian plane, this is y-axis, this is the x-axis, and the z-axis, which is referring to the K will be coming out of the page. So it will be, if it were a stick, it will be coming towards your eye. The z-axis will be coming towards your eye. Now, if you should place your eye along the y-axis, you will see the B field as this one. So if you should place your eye up here, you will see the B field or the magnetic field coming in this direction. This is how you see it. It will be circular around the charge. So at this point, the charge is coming towards your eye. Alright, so that is it for now. You can try the second positions for yourself. So this position in the Cartesian plane is 5.3 I minus 11.7 J and then 0.1 K. Go through the same procedure and you get the magnetic field at this point. For this one, the vector is already given to you. So you go straight and do your, you find the magnitude of the R, you find the unit vector of the R, you multiply it by the speed of the particle, and you go through the same procedure. Just use it as an exercise. Just watch the video again and you'll be able to do it. Alright. We come back in the second part of the video to see how small currents also produce magnetic fields.